I will talk about data science at scale. I only have 10 minutes, so it will be a very general observation. So today is very easy to fit 200 gigabytes between your fingers, but you are well aware that it is a big problem to do it in pandas. So this is the main topic of our conversation. My name is Yigal Weinberger. I'm a data scientist at the R&D team in Variant, cyber intelligence team. And I'm a lecturer in the course of Data Science Bootcamp and Dalya. And sometimes you say that every presentation is in fact an advertisement. So we have a new class of 13 very highly skilled people. They are great junior data scientists. So if you are interested, please contact me after. And my talk will be mainly focused on what I do in my day work, and which is, intelligence usually involves aggregating a large amount of data. And then you are facing a problem that even in the research stage, you need all sorts of support from IT and everything just to access the data. And this problem is very common. You can even see it today on Kaggle. This is a list of the biggest data sets in Kaggle, and you can see that some of them are very large, 80 gigabytes, which is most of the times you cannot fit it in a normal Panda data frame. And one of the solutions that you have today is, of course, using all of the scaled solutions such as Spark and Elasticsearch, but these are often involves doing a lot of IT work, and it's a lot of overhead for very early research stages. So I'm very happy that after I tried a few things, I found Dask, which help you deal with the two factors that are a big problem today when you are analyzing big data. One of them is the problem that you are unable to use larger than memory data sets. And the other is the speed of execution, which is using the parallel mode. So I think you're probably well aware of what is the basic problems of using parallelism. When you have a problem and you can think of it as a small little problems, when you feed it without parallelism to the processor, you got a bottleneck. And this caused the frustration image where you see the notebook stuck, but the processor is not working at 100%. And today we're using, most of the computers have multiple cores, and we want to eliminate this bottleneck by parallelizing the tasks. So the basic building blocks of the Dask for the parallelization is the delayed object, and I'm very happy to do it right after the decorator talk, because you can use the decorator called delayed, and this can turn this function into a delayed object. So we have the simple increment function and the simple add functions, and what we will do, we will increment 15, put it in X. Now, unlike what you will normally get, when you are assigning inc into X, you are not getting the value that returns from the functions, you are getting a delayed object assigned to this variable. And this same thing happens when you do this to y. And where we are applying the function for the two delayed objects now, we can get it into total, which you can probably assume that this is a delayed object. So currently nothing was calculated in all of this cell. But what happened is behind the scenes, the Dask created a direct acyclic graph, computational graph. It took both of the implementation of our increment function, it placed it in it fed it to the add function, and created a data graph. You can actually get, when you are using Dask, you can get this graph. It can be very complicated. This is a very simple one, but you can get whatever graphs you're using. And the only thing that will happen only once we use compute. So nothing will happen in the system until we press, we give the compute function. This will produce the result that we saw earlier. Now, based on these delayed objects, Dask has built three types of collection: the array, which is parallel to NumPy array, the which is mostly for JSON structures, unstructured data, and the data frame. I will focus on data frame because I think this is probably what interests most of us. So, as you can see, like we saw in the earlier example, the syntax is very similar to the pandas syntax. So if I want to read a CSV, I will just use a Dask function of read CSV, and I will get the train data frame. So the syntax is very similar, but there is a big change in it, because once I'll take the Dask object and apply shape to it, I will get an error, and the error will cause because we don't have a shape now. We only have the instructions of placement of data into the delayed object. So the Dask is actually used by chunks of data frames, which are normal data frames, but only chunked. We can control these the sizes of the chunks in the constructor, and you can choose them based on your system. And this will enable you to work in very specific size of the chunk that will not include all of your memory. So I don't think you can see it right now, but when you say print type of the data frame that I just loaded, the type will be Dask data frame. And if I want to get the normal pandas data frame that I'm used to it, only thing I need to do is just run compute on it, and then I get the type pandas core data frame, just a normal data frame. But there are some actions I can do without actually loading all of it in one data frame to the memory. For instance, I can use the head function and get the top values. And this is just a very short example of something that you can do and cannot do. So this is a very simple parsing of a string that is done in the upper case for a Panda data frame, and in here for the Dask data frame. It is very similar, but there is one difference. When you want to aggregate NumPy median, then I'm sure some of you are aware that median, calculating it on parallel, it's much more complicated than calculating the mean. So there are a few differences when you're working on a Dask data frame that you will have to endure in order to keep it all out of the memory. So it's not completely perfect, but it's a very, very strong tool, and it's very useful when you are using it for large data sets. So in conclusion, the Dask is meant to answer two types of problem. One of them is the parallelism, and the other one is the inability that you have to load all of the data into the memory. Now, this is a very nice graph that you can get just by running a Dask distributed and getting the localhost and the analysis. And you can see here that you can get all of the tasks that are done based on your actions. I'm sorry, I don't have the time to do a demo, but this is the, this is what you get when you are running a DAS data frame, which is very nice. Not, okay.
Hi guys. So I won't talk about algorithms, math, or stuff like that, but just something which can make your life better without algorithms. The idea is that when you have a team of people and each one of them working on a project, you would like to have some kind of standard between them. And I will tell you why you need that and how can you do that. Okay, so this is the typical data science team. Each one of them especially in like multidisciplinary companies like in Gong. So we have totally different projects, and each one of them on computer vision, one of them on text, and one of them is on speech. And each data scientist works on another project, and you want some synchronization between them, since you would like one person to work on another project and so on and so forth. And usually each one has their own definition of what is the main function and so on, and where the data is kept. So it's really hard to get inside a new. Next. So I would like to present a solution which is called Cookie Cutter. It's not only for Python, but there is a special template which was already created for Python. So Cookie Cutter, as the name suggests, is a way to have a template for a project, and then you can duplicate this template and create your own project. So the different project will look more similar than random, right? So like when you have a cookie cutter, like something which creates templates. This is why it's called like that. Next. So other people will thank you. Why? Because after a year, they will go need to fix a bug in your code, and they will immediately understand the structure and understand where are the notebooks, and where is the data, and where are the tests, and where is the training, and where is the models. Next. You also thank you, because sometimes reading your own code after a year is like reading someone else. You will understand, it will make you have better practices of thinking as a DAG, as a separating between evaluation and test and dev sets and so on. Next. And you have to remember this template, not like the cookie, it's totally non-binding. You can always change it. So if your project has some special structure that you need to get away from like the initial template, it's okay. You can always change your project not to be exactly like the template. And moreover, next, it's very flexible. So you can have both pre and post hooks to the creation of the template. So you can say, once the project is created, do this and that, or before the project is created, do this and that. So it's totally customizable. Next. So it's very easy to start. It's just a Python package called Cookie Cutter. You just pip install it, and after you install it, you can run Cookie Cutter and then the name of the template, the place where the template is. And people already work hard for us, so there is an initial data science template over there, okay? But you have to remember it's only a suggestion for how should a data science project look like. If you don't like it, you can change it. In Gong, we have our own templates. You can create any template you want, and you can store it in your Git repository, and instead of using this template, you can use another template. Next. So this is like the initial suggestion for a data science template done by others. Again, it's just a suggestion, and you can either use it or use your own. So how does it look like? After you run the cookie cutter with the template name, it creates a tree structure where the main file is called the make file, but it's not really a make file. It's like for C, where you compile stuff. Actually, in Gong, we changed it to be a Python code because we wanted more flexibility of what can it do. But this is like the entry point to the project. Everything you do through this this makefiles. Write makefile, download data from S3. So this will download all the data you've need for your project from S3, or makefile space train model, and this will train a model. So every newcomer that wants to know what are the possible function or procedures or pipelines which exist in the project, he will just say makefile help, and he or she will see all the procedures that are available. It could also have a makefile Docker, which will create a Docker for the project, or makefile space environment, which will create a Anaconda environment for the project. So it can do whatever you defined it to do. Another folder is the data folder, which is automatically in the beginning Git ignored, so the data is not in GitHub. And they also offer some differentiation between the raw data, the interim data, the process data, external data. Actually, I didn't follow the names of the folders as is, but I did follow the fact that data is separate in the project but ignored. You have the docs, the models, notebooks, references where you can put papers. So again, the year you go into the project and you don't remember the algorithm that you've used, you're already in GitHub, you know that the paper will be in references. You got reports, requirement file, which describe which packages you've used, and the source code, okay? So again, this is just a suggestion. You can either follow it or extend it or delete it and use your own template. Next. Can you go backward again? How much time do I have? 3 minutes. Okay, so can you click this? So this is the project page. Here you can read more about the logic behind the cookie cutter and why is it important. Go below, please. More, until you get to the video. Okay, just play it and maximize. So this is a demo of how does it look like. You just type cookie cutter, name of the template, and it asks you a question. I forgot about that, but you can define parameters. So every time you create a new project, it asks you questions like, what is your name? What is the project name? Where is the S3 buckets that you used for training? And whatever questions do you want it to ask? And the answer to those questions is actually injected into the files or the folder structure. So the name of the project will be the name of the folder. And in the README, the title will be automatically the name of the project, and so on and so forth. So the parameters that you've entered in this input stage will be injected into the structure of the tree wherever you want it, okay? Is this clear? Okay. Next slide, please. So I would like to, in the last minute of the talk, a little bit about Gong, and then I will pass the mic to the other person. So Gong actually takes business-to-business calls. It's long calls, not like when Hot or Telephone or stuff like that call you, which is B2C, but it's like long call when IBM sells a server to someone. And in these calls, it's usually over meeting across the web, so we have both video and audio and text. And then we use both computer vision and signal processing and speech processing as NLP to correlate between what the salesperson did and what the performance of the salesperson, to understand what makes a good salesperson, or what should a bad salesperson do in order to be better. And if you're interested in working in this environment, you can send us an email.
Okay, hi. Is my voice okay at the back? Thank you. So my name is Dalya Gartzman. I'm sponsored by Thematics, and I want to talk to you today about a project called TEMS, a textual math solver, which is a project I'm doing for Simplicico. So Simplicico is an EduTech startup company which operates a website that functions as a private math tutor. So imagine you're struggling with some function. So what you can do is go on the Simplicico website. Should we have like a sign for when you can push the, thank you. So imagine you're a student struggling with some function, and what you can do is go on the website, enter your function into the online calculator, and what Simplicico will do is they will guide you through the process of solving the question. And what we're working on now is to allow you to also be able to interact with the website in your natural language. So let's say I have 10 minutes to talk and I prepared 42 slides and I want to know how long I can spend on each slide, then Simplicico will guide me through the process of approaching this kind of question. So what I want to talk to you today is one aspect of TEMS, which reads the question and then outputs the underlying equation of the question. Obviously, I don't have 42 slides, so we can all relax and move on. So I'm going to start by touching two key pre-processing steps. I'm going to do a short overview of the neural network, which takes the question and extracts the underlying equation. Then I'm going to spend a moment about results, and then I'm going to share with you why I think all of this is relevant for all of us. So we said I have the question, and let's, before we go into the details, think about how we would approach this problem in general. So imagine you want to solve a textual math problem. Probably you want the question to be in a language that you understand. If I give you a textual math problem in French and you don't speak French, there's not much you can do about it. So the same goes for the machine. I want to first translate the question to a language that the machine understands. Next, something that I know from solving textual math problems is that something good to start with is replacing the numbers with parameters and focusing only on the structure of the question, where later on I could reintroduce the numbers into the structure that I built. So let's see how I do that in two steps. The first step is the tokenization step, which basically means that I take the question, I separate it to its words part, take away punctuation and stuff, and as I mentioned, every time I see a number in the question, I put it aside for later use, and I exchange it with a token of a variable. The next step is called an embedding. So what I'm doing is I'm putting all the words that I have in my corpus through a word-to-vec algorithm, which what it does is it takes all the words in my corpus and embeds them in a high-dimensional space that preserves, in a way, the semantic and syntactic relationships between the words. So for instance, my embedding could pick up that counting trees in a park is very similar to counting slides in a talk. And so if I have this knowledge in my understanding of the language, and I've already seen a couple of questions where I need to count trees in a park, the next time when I see a new question that I've never seen that asks me to count slides in a talk, I already know to apply the same logic that I know that is relevant for this kind of structure. Okay, so I will wrap up the previous part, which we took a question in the natural language of the user, and we transformed it to a question in a language that the machine understands, and we took the numbers aside for future use. So you already have some buzzwords on the board. TEMS is a sequence to permutation recurrent network with long short-term memory and attention, which is a mouthful, but we're going to see it's not as complicated as the title suggests. So let's break it down and see how it all fits. So we said we're starting with a question. The question is my input, that's the sequence, and the output is the permutation. And why would I want the output to be a permutation? Because I do expect that every number that I saw in the question will appear in some manner in the output equation. So let's see how I arrive from the input sequence to the output permutation. So as we mentioned, the first part is I want to translate the question from the language that the user used as input to a language that the machine understands. The next question, the next part is the recurrent neural network, which is the bulk part of this pipeline. And in this section, what happens is the machine reads the question one word at a time. This is the short-term memory part. But it also reads every word in the context in which it read. That's the long-term memory part. And the attention part is where the system, the machine also takes notice of the more important parts in the question. So let's say in the beginning of that question, I had another sentence that said, today I want to talk at the PyData Meetup. This is obviously not so relevant for the equation that I want to produce at the end. So I don't want to give it too much weight. So what the attention part does, and this is all inside this blue machine, takes more notice, takes more attention to the more significant parts of the question. Now, when I reach this part, I'm pretty confident that the machine has already figured out the structure of the question that it sees. And now I'm ready to introduce the numbers that I saw in the question in hope that it will arrange the numbers in the correct way to produce the equation that underlies the question. Now, I chose to use these large Lego blocks here because a large part of the pipeline is relied on publicly accessible tools developed by the community, such as Keras and Word2Vec, and online resources such as professional blogs and YouTube channels. And these are, so I want to use the stage to thank the community for making these increasingly complex tools increasingly accessible. So thank you for that. So let's wrap up this pipeline. We saw that we're taking a question in the user language and producing an equation in mathematical form. And what we can do is, what we normally do when we train neural networks is that we take many pairs of question and equation, and what we can see that as the system sees more questions more times, it gets better results, really has a good way of predicting the outcome equation. And okay, maybe that's it. So maybe now is a good time to wrap up. What we have is a neural network, or actually a pipeline that includes a neural network that takes, that was a spoiler, but I forgive you. That takes natural language textual math problem and produces an equation that underlies the question in order to allow Simplicico to guide students in solving the question. And a major part of the pipeline is made with publicly accessible tools, which brings me to my take-home message, which is that this is really an exciting time to be a part of the data science, machine learning, neural network community, where you can take practically any crazy idea that you have in mind, and if you know the correct tools that are publicly available, and if you understand them enough to integrate them together, you can really go as far as your imagination takes you. So thank you. One question, yes. Sorry? How did I get data? So there are some tools that use classic natural language processing tools to tackle this problem. The data sets are not as large as I hoped when I first started working on this problem, but there is some data from online resources and like crawling some question and answers websites.
Okay, thank you. Hi, my name is Diane Chang. I'm a data scientist from Intuit, also from the California office. And I'm pretty jet lagged, so if I fall asleep halfway through, just drag me into a corner and the next person can start. So I'm talking to you tonight about how we use a technique called a rule ensemble method. It's a machine learning technique that we use to help with our small business lending. So imagine that you own a small business and you have a dream. You want to open a new location. Maybe it's the first location. Maybe you're moving it out of your house or your garage. And you need some money in order to do it. If you're like most small businesses in the US at least, you would turn to your bank as the place to go to try and get some money. But unfortunately, most small businesses get turned down. We did a survey and we found that in a 2-year period, 60% of our small business customers had applied for a loan, and 70% of them were turned down. They, on average, submitted 3 applications to 3 different banks and spent about 33 hours filling in those applications, following up with questions and documents. And so this is a big problem for our small businesses. And go ahead. And why is this important to Intuit? Well, at Intuit, we build financial software for consumers and small businesses, and we want our small businesses to thrive. And so our mission is powering prosperity around the world, and we want our small businesses to prosper. Go ahead. So we have 3 different kinds of customers at Intuit. Consumers, the individuals like you and me. We have tax professionals or accountants, and we have small businesses. And we have products for each of those different types of customers, but the one I want to focus on is the small businesses. Our flagship product for small businesses is a tool called QuickBooks, which is accounting software. And in it, our small businesses can enter all of their accounting information, like their invoices, any of their expenses, their assets. All that information gets entered into QuickBooks. And then we have another business on this side that we call QuickBooks Financing that helps small businesses. Go ahead. So the purpose of QuickBooks Financing is to help small businesses get access to the money that they need to help their businesses grow. And we know that accounting data can help them. They've already entered all of the information into QuickBooks that the lenders need in order to decide if they're going to lend to them or not. And so with the customer's permission, we can use that data to help them in the lending process. Go ahead. And so one of the things we try and do, we help our lending partners determine which of our customers are the most creditworthy. And to do that, we're trying to predict whether a small business will default on a loan. And typically, when you're trying to do a prediction problem like this, in the old days, we used to build a single model. Go ahead. Thank you. So we could build a big model like a decision tree, just one decision tree, or we could build a logistic regression. But as most of you know, ensemble methods now are preferred over building this type of big model. So instead of having one big model dictator, we actually have more democracy, where we're building a lot of little models and vote, and they together determine what the outcome or the answer will be. And so the type of ensemble method that we use for small business lending is called a rule ensemble. And what do I mean by a rule? Excuse me. So these are some examples of the rules that we build. So we're looking at characteristics of a small business, and we build rules that are that you can sort of answer either yes or no, true or false. And the question that we have is, well, where do these rules come from? Go ahead. And that we use a technique very similar to a lot of ensemble methods. We build decision trees. We build a lot of little baby decision trees, and from each of those decision trees, we generate the rules. Go ahead. And so it turns out that for every node in the tree, except for the root node, every node corresponds to a rule. So as you can see here, the first branch corresponds to the first rule, or the first branch corresponds to the first 2 rules, I guess you could argue. And then as you go to the next level, you get more and more complicated rules. And so from one simple decision tree, just a 2-depth decision tree, we've already built 6 rules. Go ahead. And so you can imagine if we built a lot of little decision trees, how many rules we're going to get. So now we're stuck with a lot of rules, and we have to figure out, well, which of these rules are the most important? And we do that by assigning weights to the rules. So the rules evaluate to a true or false, a 1 or a 0. and then we weight each of the rules so that if it's true, the coefficient that's associated with that rule gets added to our score. And we build those, and we determine what those coefficients will be using logistic regression. So in a way, we're kind of combining those traditional models that I was talking about, the decision tree and the logistic regression, and we're using the decision trees to build the rules, and then the logistic regression to come up with the weights for the rules. And the form of what the rule ensemble looks like, you just are taking a direct sum of the rules that, as I said, evaluate either to a 1 or a 0, and then the coefficients are multiplied, and then you add them up. Okay. And one of the great things about doing this is that, so decision trees are really good at handling categorical variables. And linear regression is very good at handling continuous variables. And in a way, we get the advantage of having both of them with a rule ensemble, because we get the categorical variables modeled really well by the rules, and then we can also add the continuous variables here and have two sets of coefficients that we're trying to determine. The A's that are the weights on the rules, and then the B's that are the weights on the continuous variables. Go ahead. And so this is a typical kind of output that you would get from a rule ensemble. So the far column is the definition of what the rule is. And then this middle column here is the coefficient, or the weight, the A sub m's that I was showing in the previous slides. And as you can see, they could be positive or negative, so they might add to our score or detract from the score. And then we have this column here that's called the support, or STD. So if it's a continuous variable, it's the standard deviation. That's what the STD refers to. But if it's not, if it's a rule, we compute what we call the support. And the idea behind, the intuition behind the support is that you're trying to understand how much this rule affects the samples that you have. So you look at, for each sample, and you check to see, does the rule evaluate to true? And basically that means you're just adding up, you're counting the number of rules for which the rule evaluates, or you're counting up the number of of samples for which the rule is true, and then you divide it by the number of samples you have. So you're kind of getting, an idea of the weight of how often that rule evaluates to true. And then we have a final column, sorry, back up. The final column, the importance. And the importance of a rule is determined by, well, it depends. If it's a continuous variable, you look at the standard deviation and you multiply it by the absolute value of the coefficient. But if it's a rule, then you look at the absolute value of the coefficient and you multiply it by the square root of the support times 1 minus the support. And so you can see if the support is really tiny, this value is going to be small, and it just means that even though it might be a very important feature, if it doesn't affect very many of your samples, then it's not going to have that big of an impact in your model. And then if the other way around, if it's very close to 1 and it impacts almost everything, then again, it's not going to be a very distinguishing feature of your model. Okay? And then from the importance, I forgot to mention, you then just scale it. So you divide the importance, you figure out the importance for every variable, divide it by the maximum importance, multiply by 100, and then it's relative to that importance. And then from that, you can compute the importance of each of the variables or features from your model. And you do that by, if it's a continuous variable, you look at the importance of the continuous variable itself, plus you look at the importance of every rule that variable appears in. And so if, say, we were looking at time in business, and that appeared in a rule with sales growth, you would divide the importance of that rule by 2, because the time in business was only half of the impact, because there are 2 features in that rule. And then you add up so you take the importance of that rule, divide it by the number of features in that rule, and then you add it up for all the rules where the variable appears. And so the reason we chose to use rule ensembles for small business lending is that they're very easy to interpret. And with lending business in particular, there are a lot of regulations in the US about how you can lend. And if you turn somebody down, you need to be able to tell them why. You need to be able to prove to a regulator that you're not biasing based on a protected category like gender. And so the models that you're using to make these credit decisions have to be very interpretable. And they also handle missing values very well. It's part of, just being inherent part of a decision tree. One of your rules might be that the value is missing. And then it easily incorporates both categorical and linear features, as I mentioned. And it also has a strong predictive power of an ensemble method. And that's it. Do it. Thank you. One question? So what doesn't change? The economy, that's true. So the question, yep. Yes, there are definitely external factors that affect the lending business. So the question was, what about the economy? And the economy definitely has a huge impact on whether somebody defaults on the loan. But it doesn't, excuse me, it doesn't, so we take that into account as well as more of a global feature of how much risk we're willing to take on. But when we're trying to distinguish one company from another, we don't care as much about the external economy. But that's a good point. Great, thank you.
Hi everyone, I'm Tal, and today I'm gonna tell you a bit about how to build fast and powerful models with very little data by augmentation methods. So we know data is the most crucial part of our data mining and AI application exists, and the next big is deep learning. So we know that in theory an algorithm have been around for quite. However, the ability to process the right amounts of data brought us to the recent breakthrough in the field. So today I'm going to tell you not about the pre-processing stage, not about cleaning data, not about active learning or semi-supervised learning. I'm going to tell you about augmentation. Do you know what augmentation is? Awesome. Cool. So why deep learning? So we know that as the amount of data increases, the performance increases as well. So comparing to old machine learning and computer vision algorithms, it's better for us to use deep learning. And now I was wondering, how can we use data science techniques in order to scale the amount of data that we have at hand? What is the sufficient size for a neural net to give an optimal generalization? Anyone else? Uri? No? So getting the data is not an easy task, or not cheap. Some people use either annotators or mechanical Turk or Crowdflower, but it's a headache because you need to create a task and then you need to validate the data that you get back. So the problem at hand is how can we generate large synthetic data from small amounts of real data? And how can we still validate and have an AI system to learn well on it? Why is it good for us? So who here is on Kaggle? Great. So Kaggle winning classifiers all utilizing techniques to artificially increase the number of the training examples. And we know that as the algorithm is consistent like trees, like neural nets, the larger the size of n of the training set, the smaller the generalization is. Training set consists of independent draws from the same underlying distribution. We can keep drawing as long as we want, and then we construct a training set as large as we want. Lastly, data augmentation can act as a regularizer and prevent overfitting in neural networks. What are the use cases we can use for augmentation? So, as I mentioned, the imbalance class problems, it's the best case to use it. Other case would be testing and validation, and the other one is overfitting. And lastly, images. It makes the network invariant to certain transformations such as translations, flip, and so on. So the challenge is that sometimes we don't have prior knowledge on the data set at hand. So if you have a task that you already know, and the narrower as the task is, then it's easier to augment your data. However, sometimes you don't know what your data at hand, you even don't have any ground truth. The feature might vary from time to space, from one application to another, and people try to use, for instance, resampling methods such as bootstrapping, so on and so forth, but it's not really working. So there are three spaces you could think about data augmentations: 2D, images, 1D, and video. The easiest space is, of course, images. You could think of an image and then augment your data set. And originally, the data warping was used in order to balance the amount of training examples for each character class and the handwriting task. We know the data augmentation can reduce the bias in the classifier to favor more frequently presented training examples. How can we create additional training samples? Two definitions. One, the data warping, which generate additional samples through transformation applied to the data space. The other one is the synthetic oversampling, which create additional samples in the feature space. So elastic deformation in order to create augmentation in the data space is performed by defining normalization random displacement field in the images and specified a unit displacement vector. There are two other algorithms I've found in the augmentation in the feature space. The first one is SMOTE, stands for the synthetic minority oversampling technique. And the second one, which is more complicated, it's the density-based SMOTE algorithm. For the experiment, so I conducted classification architecture that was divided into two stages. The first stage included the feature generation, and the second one is the classification stage. Then I was wondering, what's better? Is it better to conduct data augmentation in the data space, or is it better to do it in the feature space? I used CNN, and I tried to perform to actually work with MNIST, and I discovered the following. I discovered it was better to perform data augmentation in the data space. I thought actually it was better to do it in the feature space, but it's better to do it in the data space as long as the label preserving transformation are known. The SMOTE algorithm can be used to perform data augmentation in the feature space. It's a more robust solution. The dbSMOTE algorithm can increase overfitting due to the algorithm creating new samples close to the existing clusters. And the improvement in the error provided is actually bounded by the equivalent amount of the real. For the implementation, I used Keras API. It's pretty straightforward. Now I move to another space, the 1D space. And then the only thing I need to keep in mind is that the characteristics of the small data set, I must actually don't destroy them. And it's very, very challenging because the vectors, the feature, they might be binary, might be numerical, might be categorical. I don't really know what are the correlations and the covariant metrics between those vectors. And I actually need to verify what are those correlations and the covariance. So I came up with three algorithms that actually I'll actually describe two of them in the next slide. The first one is based on GMM, including the BIC score. The second one, it's based on EM. The second one is the k-means clustering. I also use the silhouette measure in order to augment the clusters. The third one, which I won't cover here, is actually a more complicated algorithm where I measure all the covariance metrics by chi-square test and material information tests, and I also use R-square. So in a nutshell, I'll just describe the two-stage architecture. So the first stage is fit a clustering model. You choose a clustering model, either GMM or k-means. Then we adapt the methods for and the parameters to the shape of the data. Then we select the number of clusters, and then we select other parameters using a clustering metric. In the second stage, it's the sampling. You random the cluster, and then you generate data using random samples from the cluster in hand. The data. So as I mentioned, the data can vary, it can behave differently from one use case to another, and I came up with different cases where the data sets were pretty different from one another. It might contain numerical, categorical, binary vectors, it contain missing values. And also I might not have column specification or any prior knowledge about the data, which is sometimes hard. I tried to my algorithms with 3 data sets. The first one is sleeping patterns, acquired data from the Fitbit. The second one is the medical data, and another one is the IoT data of air conditioning. So for conclusion, augmentation advantages. First of all, increase your data set size as much as you want. Second of all, the model is more robust, and you actually can prevent overfitting. With 2D space, augmentation is better in the data space. It provides greater benefit for improving performance and reducing overfitting. The GMM-based clustering model actually produces diverse results. It might be it might be tricky because sometimes you get values which are not predicted if you have values that are near zero values. If I compare it to the k-means, you might get sampling that produce results that are not as diverse as the GMM-based algorithm. However, the boundaries of the data are respected. Thank you very much. Questions? So actually, the data space augmentation is very similar to what you mentioned, but the vector there is normalized by a strength parameter. So it's like, I guess it's more robust way to do it, but I guess it's more of the same. So sometimes you cannot use, you cannot actually estimate the density of the data. You have a data set where you have missing values and you don't really know how can you, what is the density. So I'm trying to project it to another space, and then I'm trying to find from multiple models what is the best model that fits, and then I try to sample from the best cluster just by the number of samples in the cluster. Okay, awesome. Thank you. Yeah, great question. So the classification stage, it's actually a way for me to measure what is the performance of the first augmentation part. So what I do, I actually compare it to the data set without the augmentation. This is one way. A second way is actually to train a classifier that knows how to predict an augmented data versus real data. And then if it works well, it means that you didn't do a good job. But if the classifier doesn't really know how to predict what is the augmented data, then it seems like you did a good job. תודה.